Hi, Happy New Year. In this video, I want to talk about a no free lunch theorem. There's lots of them. I'm going to talk about just one that applies to supervised learning. And what it says basically is that in order to select a supervised machine learning algorithm, you have to assume something, maybe something kind of trivial about the data, or else, if you don't assume anything about the data, there is no guarantee at all that your algorithm is going to work. Put it like that, that's completely obvious, but it's going to have a funny kind of implication. So let's start. So first of all, what's the setting? Well, you have some kind of training set, and here you have labels 1 and 0, and you have a test set. So now let's talk about what it means to not assume anything about the data. Well, where does the data come from? Well, you can imagine that there is this universe of all possible lines here, so pairs of x's and y's, right? And they all come from this set, which contains the entire universe of all possible examples. So, this line came from here, and this line came from here, and, this line, it also came from here somewhere, right? So if you assume something about the set, well, you would not have, arbitrary lines here, right? It might be that this set is like, the set of faces, and y is where x's are kind of correspond to images of faces, and y's correspond to like labels, like 1 is if it's a face of Justin Bieber, and y is 0 if it's not a face of Justin Bieber, right? And then what you'll have is, well, if x is not the face of Justin Bieber, then y can never be 1. That would be one possible assumption that you can make about this set. Another possible assumption that you can make about the set is that there's nothing to say about it. So what does it mean? It means that every line, so this line and this line and this line, every line is equally likely to come from this universe of all the possible examples. So let's make that assumption. Any line is equally likely, so in particular that means that this line is as likely as a line where the y is equal to 0 and not 1, right? So if you assume that any line is equally likely, well, we could equally have another set that's like that, where all the x's are the same, but the y's are flipped. So instead of the 1 here, we'll put a 0. Instead of a 0 here, we'll put a 1. So those came from the same source. We just kind of sampled another point and put it here, sampled another point and put it here, right? And by the way, you always want to assume, right, that the points for the training set and for the test set were obtained using the same process, or else, well, it's not a real test set for this training set. So, okay. Now, let's say that we have a machine learning algorithm, and let's call it A. Let's not get too creative. So, okay, how is this machine learning algorithm A going to do on this test set and on this test set? Well, we don't know, but we can just say, well, it's going to get alpha% of those right if it processes this training set, right? So the performance on set number 1 for test, I'm going to say, going to be alpha. Okay, so alpha% correct. So what does it do, A? Well, A takes in those guys, right? So it takes in this training set, so essentially this line and this line and this line. And then what it does is it predicts whatever label for this guy, and then we compare it to 1. And it predicts this guy, and we compare it to 0. Okay, so far so good. We assumed that it got alpha% correct. We don't know what alpha is. What about this one? So we said that we're just as likely to see this situation as we are to see this situation. And in this situation, well, the training set is the same. So A processes the same training set, and then it sees this test set. So whatever it got right over here, it'll get wrong, and vice versa. So that means that the performance on set number 2, well, it's just going to be 100 minus alpha percent. Okay? And this guy is just as likely as this guy, and in fact, for any table like that, we'll get a table like that with the labels for the test set switched or flipped, right? So what that means is that here, on average, the performance between this guy and this guy, the average performance is going to be 50%. And every situation like that is paired with a situation like that, which means that on average, in all the possible situations, the algorithm A is going to have a performance of 50%. So isn't that kind of weird? Because we didn't assume anything at all about the algorithm A. It just processed the training set and it predicted whatever it predicted for the test set and got some performance, but on average, that performance is going to be 50%. So that's kind of nice. What are the implications? Like, what went wrong? How come this algorithm gets a 50% performance? Well, what went wrong is that we assumed that this is just as likely as this. Of course, in general, if that's true, there is nothing you can do. So, for example, when we are doing k-nearest neighbors, well, we'll say, well, actually, kind of, this line looks kind of like this line. The axes are kind of nearby in the Euclidean distance sense. So what we hope is that, if k-nearest neighbors is to work, is that those labels are more likely the same than they're different. So that's one assumption that you can make. Once you make that kind of assumption, and that's the assumption that kind of underlies k-nearest neighbors, then this reasoning stops working.